Welcome back, students. In this video segment, we will cover two sections to finish up Chapter 3. We'll cover sections 3.7 and 3.9. 3.7 has to do with what's called reduction of order, and 3.9 has to do with an introduction, just scratching the surface, to numerical solutions of ordinary differential equations. So let's take a look at section 3.7 first. In section 3.7, the idea is to take a second order differential equation, a type of differential equation that we're going to spend most of our time on in chapter 4, a second order differential equation, and make a certain substitution to reduce it to a first order differential equation that we've become experts at solving by different methods. So if that didn't make sense, let's look at a specific example. Let's say we want to solve, for example, let's say y double prime plus 1 over xy prime equals 4 over x to the 4th power. Okay, so pretty clearly we can't use right away, we can't use any of the methods we've talked about so far in chapter 3 because we've only dealt with first order differential equations. But notice what happens if I make a substitution. Notice what happens if I let v equal y prime, that is dy dx, and then I differentiate both sides of this equation. Then I get dv dx equals y double prime, d squared y over dx squared. Okay, so let's see what happens if I make the substitution into the differential equation. V equals y prime, v equals dy dx, and dv dx equals the second derivative of y. So y double prime is now dv dx, and I'm substituting y prime equals v. And look at what happened to our differential equation. Look at what happened to our differential equation. Our differential equation was reduced to a first order differential equation. And this one happens to be, if you don't recognize it, take a second to think about it, recognize it. What if instead of v it had y, so it would be dy dx plus 1 over xy equals 4 over x to the 4th. It is first order linear. So we learned in first order linear that an integrating factor should be pretty much automatic to you by now, is u equals e to the integral of the coefficient of the dependent variable, in this case v, over e to the ln x. Remember, we leave off the absolute values, and that gives us x. Okay, so that transforms the left-hand side of the differential equation. The whole idea was to collapse that left side into the integrating factor times the dependent variable, in this case v instead of y, and multiplying the right-hand side by the integrating factor, we get 4 over x cubed. Okay, then we just integrate both sides with respect to x. We get xv equals the integral of 4x to the negative 3 is negative 2x to the negative 2. Okay, plus a constant of integration. By the way, we can check that. Integral 4x to the negative 3 with respect to x is 4x to the negative 2 over negative 2 plus a constant. So that works out nicely. So back to our differential equation. So the idea in solving a differential equation, though, is not to solve for the substituted variable. We're not looking for v, we're looking for y. So let's solve for v first. If you divide both sides by x, you get negative 2 over x cubed plus c1 over x. Okay, then make the substitution. V equals y prime, so dy dx equals negative 2 over x cubed plus c1 over x. Then integrate one more time to find y. It's a really clever and really kind of simple method to describe, actually. Just make the substitution v equals y prime. It would be nice if it worked for every second order differential equation. Unfortunately, it's a very small class of differential equations that it works for. So, but when it works nice. So, integral of 2 over x cubed is, I think it's 1 over x squared. And of course, we can check that. The integral of negative 2 over x cubed is the integral of negative 2x to the negative 3. So that's negative 2x to the negative 2 over negative 2 plus a constant, which is 1 over x squared plus a constant, of course. So plus, oops, get rid of that green there, plus c1 times the natural log of the absolute value of x plus c2. And it should have two constants. Second order differential equation should have two constants, should involve two constants. We'll generalize that to an nth order differential equation. Should have n constants, sort of like constants of integration, but not quite. Okay, so the idea for this particular differential equation, your author doesn't summarize this. He does not summarize this very nicely, but I will. So we were given our differential equation involved y double prime, y prime, and x. So we were given, how can we write this? We were given y double prime is some function of x and y prime. Make sure you agree with that. So we were given the differential equation. I am just all over the place here. Y double prime plus 1 over x y prime equals 4 over x to the 4th. That was our original differential equation. Gosh, I need to check it just to make sure. Yeah. Okay. So if you were to solve for y double prime, it would be a function of only x and y prime. The idea is to, in these cases, let v equal y prime, or let dy dx equal v. Okay, so that means d squared y over dx squared equals dv dx. Then make the substitution. When you make the substitution, it reduces the original differential equation to a system of differential equations, a pair of differential equations to solve. The first equation, of course, is dy dx equals v. Okay, that's the substitution, but we can't solve that until we know what v is. And when we make the substitution, the second derivative becomes dv dx. Again, the substitution right there, dv dx equals f of x and v. V is dy dx. So we get a pair of differential equations. You solve the second one first, and then for v, and then you substitute that into the first one and integrate to get the solution. Okay. Well, let's take a look at another one. Let's take a look at another problem. So for example, solve, let's say d squared y over dx squared equals dy dx quantity squared times tangent of y. Okay, so let's see what happens if we do that same substitution. Let dy dx equal v. That means d squared y over dx squared equals dv dx. Okay, making the substitution, that gives us dv dx equals, and v was dy dx or y prime, so this is v squared tangent y. And that's a problem. That is a problem. The problem is we have too many variables. Too many variables. Well, then what went wrong? What went wrong is that our differential equation is not of the form, where was it? dy dx, or I'm sorry, d squared y over dx squared equals a function of x and y prime. Our differential equation is of the form d squared y over dx squared is a function of not x and y prime, of y and y prime. And with that in mind, we are not going to be able to make the substitution and have only two variables. We have three variables, x, v, and x, v, and y. Okay, so how do we get around the problem? The solution to the problem. Solution to the problem. It's a very clever one. Well, let's go back to dy dx, or d squared y over dx squared. We're still going to make the same substitution. dy dx is v. But d squared y over dx squared is still dv dx, and that x is a problem because it contributes to having three variables, and we really have to have only two. So we're going to use the chain rule on dv dx and make it dv dy times dy dx. And you might think, oh, we still have x in there, but what is dy dx? dy dx is v. So this is dv dy v, or v dv dy. Okay, so back to our problem. Our problem was that we have dv dx. Oops. It's not dv dx. Original problem is we have d squared y over dx squared equals dy dx. dy dx squared times tangent of y. So if I make the same substitution, dy dx equals v, this is absolutely the same substitution, but I'm going to manipulate d squared y over dx squared so that it now equals v dv dy. So I get v dv dy equals v squared tangent y. Nice. I have only two variables to deal with. In fact, this differential equation is separable. So if you divide both sides by v squared, you get dv over v. Multiply both sides by dy, you get equals tangent y dy. And integrate. So I'm going to integrate and integrate. And very simple integrals on either side. The natural log of the absolute value of v. Calc 2 integral of tangent is log of secant. Plus, I'm gonna be a, I was gonna be a tricky you know what, but I won't be. I'll just say C1. Let's just say C. Okay, let's solve for v. So I'm gonna have ln v minus ln secant y equals c. So I have ln laws of logarithms v over secant y equals c. So I have absolute v over secant y equals e to the c. So I have v over secant y equals plus or minus e to the c. Same old trick as we've been using all along. So v over secant y equals, let's say, c1. So v equals c1 secant y. Well, we're not looking for v. We are looking for y. So we have v dy dx equals c1 secant y. Almost there, another separable differential equation. So we have dy over secant of y equals c1 dx. Super easy to integrate this one. 1 over secant is cosine c1 dx, and we integrate both sides. Integral cosine is integral cosine is sine. Integral c1 dx is c1 x plus d, and that's our solution. That's our solution. Let's say c1 x plus c2. That's our solution. Second order differential equation had two constants. So just to summarize this, just to summarize the whole business, this whole section, if we're given, I think that'd be a good idea. If we're given, let's say d squared y over dx squared equals f of x and dy dx, let v equal dy dx, and that transforms into the system of two differential equations, dy dx equals v, and dv dx, that's the second derivative of, it becomes the second derivative of y, equals f of x v. Okay, so it transforms into the system of two differential equations to solve. On the other hand, if we're given d squared y over dx squared is a function of y and dy dx, then do the same thing. Let v equal dy dx, just like we did before. And before, if you take the derivative of both sides, you get dv dx equals d squared y over dx squared. Same thing here. If we differentiate, we get dv dx equals d squared y over dx squared. But I don't want that dv dx in this. I don't want dv dx because it'll contribute to having three variables. X, on the right hand side, we're going to have a y and y prime as variables, y and v as variables. On the left hand side, we're going to have dv dx. So I'd like to make dv dx into a function of v and y. So this gives us d squared y over dx squared equals dv dy dx, or v dv dy. Okay, bottom line, bottom line, excuse me, our differential equation then gets turned into a system of differential equations. dy dx equals v, same as before, but not dv dx anymore. It's v dv dy equals f of, remember we were given y and dy dx, v. Okay, and then we solve this system of differential equations, of course solving the second differential equation first. Okay, and that's all I wanted to do with section 3.7. It's a very light section. 3.9 in the textbook is not a light section. It's a heavy section. But I've chosen to only cover one of the numerical solution methods in section 3.9. I want to just treat it as sort of a survey section for you. So we're only going to study one of the methods of numerical solutions to ordinary differential equations in section 3.9. Okay, so let's finish up our video segment by taking an introductory look at numerical solutions to ordinary differential equations. While we're only going to be spending a very little time on this subject, this is arguably the most important way to solve differential equations in real life applications. In real life applications, there are very few examples of problems that result in some nice differential equations that we're used to, like linear, separable, first order linear, separable, exact, etc. We learn those methods primarily so that you can study higher science courses, STEM field courses, where the problems in those courses have been made up so that they'll have solutions so that you can learn the physics or whatever it is that you're studying. Don't get me wrong, in some real life examples we do have quote unquote simple differential equations occurring, but in most applications, as far as I understand, solutions to differential equations need to be estimated or approximated. So with that in mind, let's talk about how to solve ordinary differential equations by an approximation method. The method we're going to use is called Euler's method. The very first thing I'd like you to learn is how to say Euler and not Euler. Euler's method is the name Euler is pronounced Euler, even though it looks like Euler. Okay, so what is Euler's method? What is, besides a method that doesn't seem to correspond with the name sounding the way it's spelled? Well, here it goes. Suppose we're given an initial value problem. We're given an initial value problem, something like y prime is some function of x and y. For example, y prime equals xy plus 2. That's a y prime equals some function of x and y, where I'm given an initial condition of y of 0 equals y naught. So let's say where y of 0 equals 0. And we're actually going to return to that differential equation, the one I've written in green. So the idea is not to find an explicit form of the solution, but to find the y values of the solution at specific x values. So if y equals phi of x is a solution curve, or an analytic solution or an algebraic solution, an exact solution, then we're interested only in the y values at, say, x1, x2, x3, phi of x1, phi of x2, phi of x3, phi of x4, phi of x5, etc., etc., etc. So what that means graphically is this. So get used to this picture for a second, just digest this picture. What I've got graphed for you is the solution curve. Suppose we have the solution y equals phi of x, the theoretical solution. And we're interested in phi of x1, phi of x2, phi of x3, etc., etc., etc. Okay, but we're not interested in the solution curve, just the y values on the solution at those, let's say, those 3 points to begin with. We're given one y value on the curve. We're given the initial condition y of x naught equals y naught. So we're given one y value. So the idea is to use tangent lines to estimate the solution. So here's what I'm talking about. We already have the solution y naught. We're given the solution at y naught, at x naught. It's y naught. We're given. That's what we're given. So the next thing we're interested in is to estimate phi of x1. Phi of x1, and we're going to do that by taking a tangent line, not at x1, but at the place that we know already. We already know, oops, oh, yeah, this is rough. We already know, oops, this keeps popping up. We already know, I bet it's going to pop up again. There it is. Give me a second. So you don't have to listen to me say we already know again. Oh, I did it again. I said we already know. We already know the y value at x naught. It's y naught. And we know the slope at every point on the curve. Because remember, we're given y prime equals f of x naught. So I know the slope of my solution curve from point to point. So the idea is to see that little red tangent line I've drawn, use that tangent line at the previous point to estimate y phi of x1. So I'm going to use the y value at x1, but on the tangent line to estimate my solution there. That tangent line approximation we're going to call, say, y1. And it's the y value on the tangent line at x1. So I already knew y sub 0. And now I've got an estimate to phi of x1, which is going to be y1. And it's going to be off by a little bit. Okay, and let me draw a little chart to sort of keep an eye on my approximation. So give me a second here. So I made a little chart to sort of organize things here. So let's say I is the subscript. So when I equals 0, I have x sub 0, x naught, and I have the y value on the solution curve because it was given. That's the initial condition. So there is no approximate value, and the error is there's no error. This is exact. Okay, so now let's look at x sub 1. At x sub 1, the exact y value would be phi of x sub 1. I don't have access to that. Okay, that's let's say out of our reach. Okay, this is sort of, let's do this. This would be perfect world. Perfect world. And this is reality. I have to estimate the solution. So I estimate the solution as y sub 1. I estimate the solution as y sub 1, and I get that y sub 1 by using the tangent line at the previous x value and shoot over to y sub 1 by letting x equal x sub 1 in that tangent line. Okay, so what's going to be my error? The error is going to be the absolute value of the true value of my point, the true y value of my point, phi of x1, minus the estimate, y1. Okay. So how does this method continue? The method continues by using a tangent line now at the next point, at the point where I'm currently located at where I'm considering phi of x1. But I don't have access to phi of x1. I only have access to y1. So what I'm going to do at y1 is I'm going to use another line that goes through x1, y1, and I'm going to use as a slope the differential equation evaluated at x1, y1. So I'm going to get another line. It's not letting me draw. There it is. Okay. That line is not that line is not a tangent line to the curve, but it's using a formula for the slope at the estimated point x1, y1. So it's a pretty tall order for that to be accurate. In fact, the next approximation, y2, is straying away from the solution curve by a lot more than the y1 did. Okay, y1, if you look at it, the actual y value on the curve at y value on that line missed phi of x1 by quite a little bit right here. I'm trying to make it solid in red. That little red distance is our error. Now look at y2. y2 is this y value. Look at the error now. That's the problem with with Euler's method, is that as you move on from point to point to point, your error increases, generally speaking. Okay, so how do we get phi of x3? What we do is, since we have x2, y2, we find an equation of a line through x2, y2, and use as the slope of that line the slope given by the derivative, not at phi of x2, because we don't have access to phi of x2. We use it at x2, y2. And that's going to be off. That's not going to be accurate. Okay, in fact, we lose accuracy every time we find a new solution, a new approximation to a solution point. And look what's happening. Look at our error now. This y value that I'm drawing here, this is y3. y3 is the y value on the line, and we're using that y value to estimate phi of x3. That's right here. That's y3. And look at the error. The error is this shaded amount. It's phi of x3 minus y3 in absolute value. This was y2. So as we find more and more and more y values, or estimate more and more y values, they theoretically get worse and worse and worse error-wise. At x2, we have the actual value phi of x2. We have the approximation of y2. We have the error as the true value phi of x2 minus y2, and it's that thicker, the second thicker red vertical shaded portion in there. And finally at x3, or at I equals 3, we have x3. True value would be phi of x3, way up top on the solution curve. We estimate the phi of x3 by using y3, and that y3 we get by using a tangent line at the estimate, our previous estimate at y2. So our error seems to be compounding. These estimates are getting worse and worse in terms of error as we move from point to point to point. Okay, so is this a valuable method? Yeah, it is. If we choose our x values to be x1, x2, x3, etc., to be close to x naught, that will mitigate the errors a little bit. In fact, quite a bit. If we choose them extremely close, then those errors are going to be, well, they're still going to be increasing, but they'll be substantially smaller. There are better methods. This method uses lines to estimate the true solution curve. If we bent those lines up and used parabolas, sort of the kind of thinking we did with Simpson's rule in Calc 2, we might get better. We might get better results. So let's use Euler's method to estimate the solution. Okay. Well, I really haven't developed Euler's method yet, so let's do it. I'm going to want to use my drawing. So I'm going to get rid of my chart. You can always come back to this chart if you'd like, by coming back on the video. So I'm going to get rid of all this because I want to work in this area. Okay. Oops. All right. Gone. If you noticed, I copied it just in case I need it again. Okay, so let's find y1. Let's find y1. Let's call y1 the result of using line L1 that I have pictured there, L1. Okay, well, at the line L1 requires a point and a slope. I have a point, x naught, y naught, and I have a slope. Slope is y prime equals f of x naught, y naught. Remember, the differential equation provides us with the slope. So the equation of the line is, using the point slope form of a line, y minus y naught equals m, the slope, f of x naught, y naught, times x minus x naught. That's the line L2. If you solve for y, you get y equals y naught plus f of x naught, y naught, times x minus x naught. So what is my first approximate value? It's y1. y1 then equals, I don't know why I moved it over, y1 then equals y naught plus f of x naught, y naught, times x1 minus x naught. That is my first approximation. Okay, now I'm going to find L2 to find y2. Okay, L2 requires a point and a slope. The point, and this is where our error starts to compound, our point is not x1, phi of x1, because I don't get phi of x1. I'm using the estimated point, so I'm introducing error right from the get-go, right from the beginning. And I'm going to compound that error with the slope. I'm not finding the slope at x1 phi of x1. I'm finding the slope at x1 y1 using the slope formula. Hopefully the slope doesn't deviate too much from the true slope there. It may. Okay. Okay. So f of x1, y1 is my slope. The equation of L2 then is y minus y1 equals slope f of x1, y1 times x minus x1. And solve for y. You get y equals y1 plus f of x1, y1. Oops, it's too sloppy. F of x1, y1, x minus x1. Now to find y2, I substitute x2 into it. I'm going to shoot from the point x1, y1 to the point x2, y2 along that line by substituting substituting x equals x2. So y2 equals y1 plus f of x1, y1 times x2 minus x1. Okay, so I would like to be able to do this without having to find an equation of a line every time and then put in the next x value. I want you to notice the structure of our estimates. I'm gonna attempt to copy them. I'm gonna lose my previously copied thing. That's okay. I'm gonna give me a second. I'll be right back. I just printed the wrong thing. Okay, I cleaned it up. So I'm going to print my y sub 1. I just want to put the estimates y sub 1 and y sub 2 close to each other so you can see sort of a pattern. So there's y sub 1. Okay. And here's y sub 2. Let me just move it down here. I'm looking for a pattern. Okay. Look at y1. y1 equals y0 plus f of x0 y0 times x1 minus x0. y2 is y1 plus f of x1 y1 times x2 minus x1. So according to these two examples for a pattern, it looks like y3 should equal, well, y3 should equal y2. It looks like it's always one less, plus f of x2 y2 times x3 minus x2. And that's in fact true. I would like a way of getting a general formula that will allow me to bypass the finding of tangent lines altogether. Well, there it is. There's a pattern formed. So here's Euler's method. Euler's method. Euler's method. Y naught equals y naught, obviously. That's what that one's given. The next ones are given by this formula. The n plus first y value, y sub n plus 1, should equal 1 less than y value sub 1 less than that, plus the slope given by the derivative of x sub n y sub n times x sub n plus 1 minus x sub n. That is Euler's method. That is Euler's method. Okay, so let's solve a problem. Let's estimate the solutions to a problem. Okay, so let me write the problem out. So here's our problem. Estimate the solution to y prime equals xy plus 2, y of 0 equals 0, so there's our initial condition, and there are our target x values. So this x1 is 0.1, x2 is 0.2, x3 is 0.4, and x4 is 0.5. Okay, of course we're given y of x naught equals y naught, and f of xy equals xy plus 2. Okay, I'm going to separate this off from our previous work. Okay, so let's do it. Well, let's see. The first thing I would like is y sub 1. y1 equals, well, what does y1 equal? It equals 1 less than that subscript y naught plus f of x naught y naught times x1 minus x naught. Okay, well, y naught is 0, that's given. X naught is 0, y naught is 0, x1 is 0.1, x naught is 0. Okay, so this, well, 0 plus f of 0, 0 is 0 times 0 plus 2. Remember, f of xy is xy plus 2 times 0.1 minus 0 is 0.1. So my first y value, my first solution value is 0.2. Okay, so I want y2, y3, and y4. So y2 equals y1 plus f of x1 y1 times x2 minus x1. Okay, so here's where our solution starts to go bad on us in terms of error. y1 was an approximation, and we're using that to build another approximation. So we're going to be compounding error plus f of x1 0.1, and then we're putting that approximation into the formula for the derivative times x2 0.2 minus x1 0.1. So this is 0.2 plus the solution is xy plus 2. So so the derivative is xy plus 2. F of xy is xy plus 2. So it's x 0.1, y 0.2 plus 2 times 0.2 minus 0.1, which is 0.1. Okay, so this is 0.2 plus 2.02 times 0.1, or 0.2 plus 0.202, or 0.402. So we now have two approximate y values, and I can pretty much sure that y2 is going to be less accurate than y1, and y3 will be less accurate than y2 or y1. So y3 equals y2 plus f of x2 y2 times x3 minus x2, or 0.402 plus oops, I think I'll keep with my steps, plus f of x2 0.2 y2 0.402 times x3 0.4 minus x2 0.2, or 0.402. Now I have the function f of xy now is x y plus 2 times 0.2. At this point I used my calculator to get the solution value. So this is because the decimals start getting pretty wild, 81808. Okay, and finally y sub 4. I want y sub 4, which is y sub 3 plus f of x sub 3 y sub 3 times x sub 4 minus x sub 3. So this really flows after a while. It's not really exciting. In fact, this could become very tedious, but computers have no problem dealing with these kinds of numbers, okay, or these kinds of expressions. So by 3.81808 plus f of x 3.4 for y 3.81808 times x4 minus x3. 0.5 was x4, I believe, minus 0.4. Okay, or 0.81808 plus f of xy is x y plus 2 times 0.1. Calculator gives us 1.0508032. So that's how the method works. I want to do something that your author doesn't spend too much time doing, and I'd like you to study this example and try this on your homework as well. I want to estimate error. I want to see what's going on with the error. Okay, so what I'm going to do is I'm going to find the exact solution, and I'm going to fill in that little chart that I had before with error values. So I want to find the exact solution. Exact solution. Okay. So generally we don't get to compute error this way. Error analysis is wicked difficult because we don't have access generally to the exact solution. But this one we will. We've solved this kind of differential equation before. Do you recognize it? It's not separable. And it's not exact. It's first order linear. If you move the xy term to the left-hand side, it's first order linear. Okay, we get an integrating factor of e to the integral of negative x, or e to the negative x squared over 2. So we get the left-hand side collapses into the derivative with respect to x of the integrating factor times y equals 2e to the negative x squared over 2. And this is not a nice case. This is not a nice case at all. We looked at one of these cases before. We can't integrate e to the negative x squared over 2. So the little trick I showed you in the last video segment, or a couple video segments ago maybe, was to switch to the variable t all around. So rewrite this last form with the integral t, then integrate with respect to t on both sides. Integrate both sides with respect to t. So if you integrate the left-hand side with respect to t, and a definite integral from 0 to x, and then integrate the right-hand side with respect to t, also between 0 and x, we sort of build a solution, the best we can do kind of solution. On the left-hand side, if you use the fundamental theorem, substitute the upper limit of integration, then substitute the lower limit of integration, e to the 0 is 1, and I integrated from 0 to t x, and not from 5 to x, or 7 to x, or pi to x, because I'm given the initial condition at 0. Y of 0 was 0, so in this case we're off the hook for that. If you multiply both sides by e to the positive x squared over 2, you get the solution. E to the x squared over 2, oops, it's a radius looking integral sign I've drawn today. 0 to x, e to the minus t squared over 2 dt. That's the best we can do. Now, I'm going to use this exact solution to construct a little chart that will show us the error propagating and getting worse and worse and worse. Okay, and I'd like you to do this on, again, I'm repeating this, but I'd like you to try this on your homework too. I don't think your author asks you for this analysis, but I'd like you to do it. It's good for you. It's very good for you. So we start out with, let's say, let's do this. Let me start that chart exactly the way I did before. Start out with an I value, then an x sub I value we get out of there, then we get a y sub I value out of there. Let's say we get a true value, phi of x sub I, true value. That phi of x sub I will be from our function. How are we going to get those values? You get them on your calculator. Get them from your calculator. You can enter this function in your calculator, including the integral. And the TI-84s will do that very nicely. I'm sure the Inspires or higher level Texas Instruments calculators will do it too. So play around with it. I would. Y sub I is the approximate solution, and then my error. My error is, I think it's often referred to as absolute error, because error is really true value minus estimate. So this is sort of the absolute error. And let's fill in this chart. So I'm going to have I equals 0, 1, 2, 3, and 4. So I'm going to have x naught. Oh, that's fine. I don't need to do that. X naught is 0. Then x1 is 0.1, x2 is 0.2. Our other x values are not 0.3 and 0.4. It's 0.4 and 0.5. Yeah, that's better. Okay. So, let's see. Okay, and let's see. The actual solution is y naught, and we knew that. y sub I is 0. There's no error. It's just the initial point we're given. So at point 1, in my calculator, I computed the actual solution value as 0.20067. You might want to try to do this on your own, okay, and see if you get these same values. Enter in your graphing calculator y1 as the solution that I have right here, red arrow. And you can find the integral under Math in the graphing calculator 9. Okay, so 0.2, this is probably one of the only places in the course where you need to use that required graphing calculator. Y sub I, let's see, we computed as not red, 0.2. 0.2. And the error, if you subtract and take absolute values, is 0.00067. Okay, or approximately, let's say 0.0007. So we have 3 decimal places of accuracy. Okay, as indicated by the 3 zeros in the error. Okay, so we get about 3 decimal places of accuracy with that first approximation. So in my calculator, I entered 0.2 and computed the actual solution as 0.40538. Our estimate above was 0.402. The error is 0.00338, or approximately, let's say, just 0.003. And that gives us 2 decimal places of accuracy. We can just look at the numbers. We get 2 decimal places of accuracy. So we get less accuracy. In the previous approximation, we got 3 decimal places. Now we have 2 decimal places of accuracy. So our predictions are bearing true that the error should get worse in general. So I got an exact value of 0.84406 at 0.4. We got 0.81808 above. The error, absolute error, is 0.02598, or just rounding off, you get 0.03. We got 1 decimal place. We're losing decimal places of accuracy. Finally, the actual value at, and I've rounded off my actual values here to 5 decimal places of accuracy. So 0.0877. I took 5 decimal places. 0.0, let's see, I have it right in my screen. 0.8765. 0.876. I'll just use 1.0877. We got our estimate was 1.05032. Error is about 0.0368968, or just rounding off 0.04. So we kept 1 decimal place of accuracy, but our approximations got worse and worse and worse and worse and worse. We went from 3 decimal places to 2 decimal place, and leveled off maybe at 1 decimal place of accuracy. So if we were to take more and more x values, we'd probably lose more and more decimal places. Okay, so the method is not the best of methods. There are a lot of methods that successively get worse, but they get worse more slowly. You could use higher order approximations, that is, use parabolas or cubics and 4th degree, and that's what we're not going to cover from section 3.9. 3.9, your author will go on into using Taylor methods, and he uses Taylor polynomials or partial sums of a Taylor series to get better and better and better approximations and stuff like that. We'll stop our course with linear approximations, or Euler's method. And that brings us to the end of our section. So go ahead and start, if you will, as soon as you can, homework from sections 3.7 and 3.9. And I'm looking forward, as usual, to talking with you all again soon.